So in this video I'll go through a possible intuition, kind of like a general idea behind quantum mechanics, or at least the uncertainty principle. This won't be rigorous or logical or anything. It might not even be correct, so feel free to let me know in the comments if this interpretation isn't accurate, because it might not be. But intuitively, the way I think of the Heisenberg uncertainty principle, right? So just to go through like the overview, if you know the position of the particle, then you know, if you know more about the position of the particle, then you know less about the momentum of the particle, and then vice versa. The way I think of it, let's say we start here in the middle. So let's say this is particle P. At any slice of time, right? Let's just say this is like time equals 1. It doesn't matter what the time is or the units, but just say time is 1. So at time 1, we know that the particle is here, but then we don't know, if we know the particle is here, we don't know if it's going this way or this way. So I'll just draw arrows like this way or this way or this way, or right, there's all these possibilities, right? But then let's say at time 2, so now let's say time equals 2, and then let's erase those arrows just for a sec. I like to think of the arrows and the particles as two separate things. So when we don't know position, when we know the position, right? When we know the position, we don't really know the momentum, the direction the particle is going. So now let's say we know that the particle is going this way. I'll draw it here, like this way, diagonally to the right and up. But the particle could be here, right? It could be here, it could be here, it could be here, or it could be here, right? So we know the direction, but we don't know the position, like which position the particle is in. And so the way I kind of see it, the arrows, right? The arrows that indicate the direction of the particle is a separate thing from the particle themselves. So if I kind of like sketch a drawing, like let's say there's four positions or possible positions a particle could be in. I guess it kind of reminds me of a graph theory, but where these arrows, the arrows themselves are an object. So I guess I can draw something like in X to represent all the arrows, right? So there's 1, 2, 3, 4 particles, and then 1, 2, 3, 4 arrows, right? Of course they have, this direction or that direction, so they can be going. You can think of it like positive and negative direction, but basically, the way I like to think of the uncertainty principle, like the particles and the relationship, right? The directions going between them, right? So both of them, the particles and the directions, are both separate objects of themselves, right? So I just think of them as separate objects. And so with that foundation, going back to like this diagram, kind of like in the way I think of it, I think of the uncertainty principle, like intuitively, would be where at every slice of time, I don't know what happened previously, right? So at time equals 2, I don't know about time equals 1 or time equals 3, right? Their question. No, I have no idea what happened, right? They don't exist, basically. Each of these are separate timelines, right? This one's separate, this one's separate, this one's separate. Because it's a change, in time. I'm not being very accurate in my description, of course, but just intuitively, I just think of these as like different slices of time, right? Each slice of time is separate. And then at each moment in time, I only know either, if I know the position, right? So let's say this is the position of the particle. I have no idea where it's going, right? Because it's a slice of time, right? I have no idea how the particle, right? I have no idea whether it's going this way or this way, because it's an individual slice, right? A separate slice of time, right? So I have no idea. But if I know, like, let's say, like, if I know that this is the momentum, right? So this is the direction in which the particle is going, but since each of these are separate slices of time, right? Separate slices of time, it could the particle could have ended up here or here or here or here, right? There's no previous history to tell us it went from here to here, right? So maybe, right? Maybe the particle started here and it went up here, right? So now we know the momentum, but because each of these are different slices of time, right? The past doesn't exist, and the future doesn't exist as well, right? It's only this slice of time. So we either only know the direction, so the momentum, or we only know the position, right? Because it's a separate slice of time, we don't know both at the same time. And that's kind of like the way I see it intuitively. This could be inaccurate. As I said, it's not logical, like, at all, right? It's not mathematically rigorous, but this is the way I see it intuitively. And then this is just kind of like a bit of my afterthoughts. But the way I think of quantum mechanics, I actually think of it in terms of like Noether's theorem and invariances. So there's like a more subtle symmetry going on here where position and momentum, I know mathematically there's like a much more deeper relationship between them, but to put it very simply, they're both the same thing. It's just on they're like polar opposites of each other. So there's the simple definition of an invariant, right? Of an invariant is that it's something that doesn't change, right? It's something that doesn't change within a certain framework, right? So, for example, if we have something like, let's say, let's say angular momentum, right? So angular momentum. So we have something spinning around, right? Think of this as a perfect circle. So with angular momentum, what doesn't change is, of course, the distance, right? The distance between the particle, right, and the center, right, where it's rotating around, right? So the movement, to put it really simply, right, without any terminology, right, the movement is invariant to the center, right? It's always the same distance from the center, right? If you have the same angular momentum, of course, without talking about changing velocity, right? If you change the velocity, you change the radius, without talking about that, right? At its most simple definition, right? The movement doesn't change with respect to the radius, right? The radius is exactly the same, right? So that's an invariant. And I think something very similar is happening here, where there's like an invariant between position and momentum, right? There's some very abstract concept that doesn't change between position and momentum. It's just position and momentum are two sides of the same coin, right? They're the same thing. It's just one is kind of like an inverse relation of the other. Of course, that's how that's the whole point of Noether's theorem, right? Combining conservation laws, right? Conservation of energy, conservation of momentum with certain symmetries, right? So like angular momentum's this rotational symmetry, right? Angular momentum's rotational symmetry. Energy is energy's symmetry in terms translational, I believe. Symmetry. No, momentum's translational symmetry, but there's some very subtle invariant going on here, and I don't know enough to explain that invariance. Someone else might know, though. And another way I think of it, position, right? Position, put it very simply, right? It's just space, right? So it's space. Momentum is like time, right? So there's some sort of relation between space and time, right? It's a change of space, right? Change in space, delta space, and then change in time, right? Delta time. So there's some sort of relation between space and time that I don't know enough about to explain it. Right? I'm pretty sure someone knows about it and someone wrote about it. And I'll do more research as well. But if someone does know in the comments, let me know. And I say that because this is where it gets really interesting, right? So we have like general relativity, right, where space-time, right, is just one. It's actually one entity, right? When you bend space, you bend time, and when you bend time, you bend space. And then, right now, of course, the big thing in physics is to combine quantum, right? This is quantum. Well, the basics, the quantum, to combine quantum mechanics with relativity, right? So there's some sort of very subtle relation, right, between space and time, right? One is change, right? One is change in space and time. One is space being inverse to time, right? The more space you pass through, the less time you. Sorry, that's not correct. The faster your velocity, right? Faster your velocity. So when you increase velocity, you decrease the amount of time that passes, right? So there's some sort of relationship between these components, and there's a couple ways to describe it. People describe it in terms of like geometry, right? So like Minkowski space, which has certain invariances, right? There's Lorentz invariance. Without getting too complicated, there's some sort of very simple, elegant relationship between quantum invariance and then relativity invariance. I've been thinking about it a lot, and I'm still trying to figure it out too. But if anyone has any ideas about this relationship, please let me know, because I'd be really interested to read this. And I've been sifting through a lot of academic papers as well. And the terminology, of course, of these papers are very hard to read. So, but yeah, I believe there's some sort of like a relation between these. It's very hard to like tease it out. But this is kind of like how I see it intuitively. And if my explanation needs more work, or if I have to go into more details, please let me know, because I'd love to explore this topic a lot more.